Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
Great to be back.
Today we are diving deep into a topic that honestly most people never think about, but it basically dictates the quality and yield of products across, well, the entire chemical industry. We're talking about industrial mixing.
That's right. And if you think mixing is just, dropping a blender in a tank and hitting on, you're in for a surprise. We're moving way past basic stirring. Today we're really peeling back the layers on the rigorous engineering correlations that govern how quickly something blends, how you suspend solids, and this is the big one, how you manage complex chemical reactions inside that tank.
And the sources for this deep dive are,
they're
pretty meaty. We've pulled from a big industry handbook on mixing, all the design rules, the correlations, the stuff engineers are actually using every day.
It's dense, for sure. But our mission, really, for you, the listener, is to distill this down. We want to pull out the critical metrics, things like dimensionless blend time, just suspended speed, and, yes, the famous Damköhler number.
The goal is to arm you with what you need to design or rate mixing equipment, so you don't get completely overwhelmed by the fluid dynamics.
Exactly. And so you can spot the big failure modes before they happen.
Okay, let's unpack this. We should probably start with the simplest duty, just blending fluids.
Makes sense. Let's look at standard agitated vessels. We'll focus on Newtonian fluids, mostly in the turbulent regime.
So Reynolds number over 200, or somewhere in that transitional zone.
Yep. And when you're talking performance, the main measurement is time. How long does it take to get everything homogeneous? To make that useful across different scales, we use the dimensionless blend time.
Which is quantified as n theta 95.
Exactly. It's the impeller speed.
Yeah.
N times the time it takes to get to 95% homogeneity, which is theta 95. And what's really interesting here is that in a fully turbulent system, that number n theta 95 is usually a constant.
So if you spin the impeller faster, the blend time gets shorter, and the product of the two stays the same.
That's the theory. It sounds nice and simple.
But I'm guessing the real world has a twist. Where does that simplicity fall apart?
It falls apart when you look at the whole vessel. That constant might hold true right under the impeller, but some really important research, especially out of Cranfield, showed a huge flaw in just relying on that.
Oh, what did they find?
They found that the overall blend time is actually controlled by the slowest moving part of the fluid, and that's always in the least agitated spot, typically the pocket of fluid right behind a baffle.
Ah, so you stick your probe in the middle of the tank and you think you're done in 60 seconds.
Right.
But meanwhile, that pocket behind the baffle is still, I don't know, at 10% mixed. 5 minutes later, you've just made a bad batch.
Precisely. That local blend time behind the baffle shoots up as the Reynolds number drops. It's a huge deal in the transitional regime. You have to design for the worst-case pocket, not the average.
Okay, let's pivot to something that I found, well, truly counterintuitive. The efficiency of the impeller itself.
Oh, yeah.
We're always told these complex hydrofoils are way superior.
And for some things, like mass transfer, they are. But for simple liquid blending in the turbulent regime, the engineering conclusion is surprisingly blunt.
Which is?
All impellers of the same diameter are equally energy efficient.
Wait, I have to challenge that. Why would companies spend millions developing proprietary blades if a simple flat turbine is just as good for blending?
Because the physics of turbulent mixing are, well, relentless. The analysis shows that any impeller of a given diameter will give you the same blend time for the same power per unit mass. There's a correlation that locks it in.
What does that look like?
It's the power number, p sub o, to the 1/3 power, times n theta 95, times the ratio of the impeller to tank diameter squared. And all of that equals like 5.2. It's a constant.
So you're saying if I put a certain amount of power into the tank, my mixing time is fixed no matter how fancy the blade is, as long as the diameter is the same.
In that fully turbulent zone, yes. It's all about the power you put in. Now, that all changes in the transitional regime.
When things get thick and viscous.
Exactly. There, the blend time becomes proportional to viscosity. And this is the key takeaway. In that regime, increasing the impeller diameter gives you a much shorter blend time for the same power input.
So size matters more than shape when you're fighting viscosity. That's a great practical nugget.
Okay, so if blending is about flow patterns, let's move to where mechanical design is. Just everything. handling solids.
Right, we're moving from a single phase to solid-liquid mixing.
Yeah.
The stakes get a lot higher here.
They really do. You're not just trying to make it homogeneous. You're fighting gravity to stop expensive catalysts or crystals from just settling on the bottom and doing nothing.
You're trying to create a stable slurry.
A stable slurry, exactly. You have to suspend the solids, resuspend them if they've settled, break up clumps, and, maximize mass transfer at the surface.
And the difficulty there is tied to all the physical properties: viscosity, density, particle size, and shape. It's a mess of variables.
It is. The rule of thumb is simple. Bigger, denser solids are harder to suspend. But engineering this requires a specific number.
And that gets us to the key metric, the just suspended speed, NJS.
NJS. It's the absolute minimum impeller speed you need to lift every last particle off the vessel bottom. And to predict it, engineers lean very heavily on this Wiedering correlation. It's a workhorse.
I remember that one. It relies on a constant S, right? And S seems to just absorb all the geometric complexity.
It really does. NJS is super sensitive to that Wiedering constant, S, which changes with impeller type, its diameter, and its clearance from the bottom. You change the clearance by an inch, S changes, and your required speed could jump up significantly.
And speaking of geometry, the shape of the vessel bottom itself is a huge factor.
Oh, it's transformative. Dished-bottomed vessels are strongly preferred. They eliminate the sharp corners you get in a flat-bottom tank.
Which creates dead zones.
Exactly. Dead zones where the wall meets the base. Solids just love to collect there, form a little fillet, and completely drop out of circulation.
And you can't get them back.
You have to work much, much harder to get them back. The sources say your NJS is easily 10 to 20% higher in a flat-bottomed vessel just to fight those dead zones. That's a huge power increase.
Now let's make it even more complicated. What if we add gas? A three-phase system.
That's where, the complexity just explodes. Gas bubbles interfere with the liquid flow. They generally mean you need an even higher NJS. You have to spin faster just to fight the gas.
But the sources warn about something called a sudden collapse of the suspension. That sounds bad.
It's catastrophic. Picture this. Your reactor's running fine, solids are suspended, you start increasing the gas flow to feed the reaction, and you hit a critical point.
Yeah.
And suddenly, the whole system is dominated by the gas buoyancy. The impeller's flow is just overwhelmed. All your expensive catalyst just crashes to the bottom of the tank. The suspension is gone.
And your reaction dies. Or worse, if it's exothermic, it runs away because you've lost all your heat transfer. That really highlights why you need to do pilot tests for these systems.
And that need for precision brings us perfectly to chemical reactions, where mixing isn't just about homogeneity. It can actually be the thing that determines the rate of the chemistry itself.
We're talking about when mixing is basically in a race with the chemistry.
Yeah.
Those fast, mixing-sensitive, competitive, consecutive reactions.
Exactly. Think about it like this. A plus B makes your product R. But your product R can also react with B to make a waste product, S.
Okay.
If you add B to the tank and it doesn't mix instantly, you get these pockets of super high B concentration. Before that B can find A, it finds your precious product R and turns it into waste. Your yield just tanks.
So you need a way to quantify that race. And that's where that dimensionless number comes in. The Damköhler number for mixing, TAP.
Yes, DAM. It's the ratio of the mixing time, tau m, divided by the reaction time, tau r. If that number is large, say bigger than 10, that's a huge red flag. It means mixing is the slow step. It means you're actively destroying your own product.
And we learned earlier that you absolutely can't use the bulk blend time for this. It has to be local mixing.
It has to be. The damage happens at the molecular level, right where you add the reactant. You have to think about mixing on 3 scales. There is macro mixing. That's the bulk circulation.
Then what?
Then mesomixing, the intermediate scale. That's the initial breakup of the reactant plume as it enters the tank. But the real decider, the hero or the villain, is micromixing.
That's the smallest scale.
The absolute smallest. It's controlled by molecular diffusion way down at the Kolmogorov scale in these tiny little eddies. This is the stage that sets your final product selectivity because it's where the molecules actually meet. If this stage is too slow, your DAM is high and your yield is garbage.
So if it all comes down to that tiny scale, what does that mean for the person running the reactor? Is it just about a bigger motor?
It's more about placement. The number one rule for these systems is always add your reactive ingredient to the point of highest local turbulence, the spot with the maximum energy dissipation, what engineers call epsilon.
So don't just dump it in the top.
Never. If you feed it into a quiet zone, you guarantee poor micromixing and you're just throwing yield away.
And for scale up, You can't just make a bigger version of the pilot reactor.
No, that almost never works for these reactions. You have to scale up based on maintaining a constant power per unit volume. Or, even better, maintaining a constant turbulent energy dissipation rate right there in the feed zone. That's what controls that critical micromixing time.
This gets even trickier with heterogeneous reactions, right? When you have multiple phases, and mass transfer is another layer.
That's right. Take a hydrogenation reaction. You have hydrogen gas, a solid catalyst, and a liquid. If your mixing is bad, you can't get the gas bubbles small enough or spread them around.
Your mass transfer rate, the KLA, is terrible.
Where KLA is terrible.
Yeah.
The hydrogen can't get from the bubble to the catalyst fast enough. The reaction either crawls along, or worse, if there's a side reaction that likes high temperatures, you start making junk.
And this is where changing the physical setup, the geometry, can be a total game changer.
Absolutely. The sources talk about cases where just switching to, say, dual turbines or adding hardware to pull gas down from the surface, it can dramatically boost the hydrogen uptake rate. You turn a failing reaction into a successful one, not with chemistry, but with pure mechanical engineering. So if we pull all this together, our trip through industrial mixing really shows that good design isn't guesswork. It's about meticulous attention to really three critical dimensionless numbers.
We've got N theta 95 for blending, but remember you have to design for that dead zone behind the baffle.
Yep. Then we have NJS for solids, seeing how much something as simple as a dish bottom can help.
And finally, the big one for reactions, the Damköhler number. It shows that scale-up is all about controlling that local energy dissipation epsilon to manage what's happening at the molecular scale.
Right. It's about micromixing.
What's really striking is how often the solution comes down to optimizing the flow in one tiny specific region of the tank, not just the big picture average.
That's the core of it. Knowing where your mixing time is competitive with your reaction time, that is the shortcut to avoiding incredibly expensive scale-up failures. You can't cheat that ratio of tau m over tau r.
That makes perfect sense. And that brings us to our final provocative thought for you to think about. The sources mention that even now, with all our computing power, high-fidelity simulations, CFD, they still struggle. They struggle to accurately predict critical things in these multi-phase systems, like bubble sizes or that all-important local turbulence epsilon.
So here's the question. If predicting something like the mass transfer coefficient, KLA, is absolutely essential for scaling up these fast, complex reactions, and our best simulations still can't reliably model it, how much longer will expensive physical pilot testing remain functionally irreplaceable for guaranteeing yield and safety? Is the pilot plant on its way out, or is it just waiting for a true quantum leap in how we model turbulence?